Okay, this is from a talk by Lawrence Krauss entitled Opportunities in Cosmology, and this segment shows him starting from an equation in Newtonian physics, which he's going to manipulate around a bit, and it's just going to end up as the same maths as general relativity. So let's proceed.
But once we know that the universe is expanding, the big question, and it was the question that fascinated me when I was your age, and one of the reasons I went into the kind of physics I went into was I wanted to be the first person to know how the universe would end. It seemed like a good idea at the time. And it turns out, you'll see that my ideas were quite misplaced, but it turns out that the answer to that question is the same as the answer to a question in an introductory physics class. If I had the coin, oh, I do have a coin. Okay, so we teach you, you've all been through this, but we teach you, if you throw a coin up and it comes back down, if you throw it up faster, it takes longer to come back down. If I threw it up really fast and there were no ceilings here, it would escape the Earth. And as all of you undoubtedly know, we turned this into bookkeeping in physics. Okay? We write down the total energy of the coin, gravitational energy, to be its kinetic energy, the positive piece, and the negative piece, the gravitational potential energy.
And this is what Newtonian physics gives. So this is a Newtonian physics equation of kinetic energy and potential energy.
From the Earth. And then we just turn it into a bookkeeping problem. We look at those two energies, one positive, one negative, and we say, well, if the total energy is greater than zero, the coin will escape. If the total energy is less than zero, the coin will return. It's simple. So it's just bookkeeping. We add up the total energy. And by the way, when we set them exactly equal, we get the total gravitational energy zero. That's the escape velocity from the Earth. So we set that term equal to that term. That determines the escape velocity of the Earth, which you understand, see the masses cancel out, and we get a velocity of 11 kilometers per second. And that's how we determine, that's how we give NASA the information of what they need to know to how fast to send a rocket ship up if it's going to escape from the Earth. It's just bookkeeping. Okay. Well, we can do the same for the universe. Here's a picture of say, Hubble's picture and here's a galaxy and a bunch of galaxies nearby. And if the universe is the same everywhere, as I just told you it is, then what happens to every galaxy will happen to any galaxy, or vice versa. So if we want to find out if the universe is going to expand forever, all we have to do is look at a single galaxy and ask, is it going to continue to move away from us forever, or is it going to stop and come back? And then, as long as this region is small compared to the size of the universe, so effects of relativity are not important, we can just do the Newtonian calculation that you've all done in high school. We can say, okay, let's ask what the total gravitational energy of that galaxy is. The positive piece is its kinetic energy, is its velocity. But that, Mr. Hubble told us that. Because you measure the distance, you know its velocity. So the velocity squared is proportional to the Hubble constant squared. The negative piece is all the mass within the sphere centered on us, if we're asking if it's going to escape from us, and that's the total mass within that sphere, which depends on the density of material. So all we have to do is compare those two things. If it's a homework assignment tonight. Get a telescope, go out and measure the Hubble constant in the first part of the evening, and then the second part of the evening determine the density of matter in our nearby region of the universe, and then compare the two. And if B over A is bigger than 1, if this term is bigger than that term, then this object, you'd think, would just collapse, just like a coin will come back. If B over A is less than 1, so the positive piece beats the negative piece, it'll expand forever. So really, the holy grail, as I say, of cosmology was to measure over the course of the 20th century these two pieces. One of the reasons we needed to know the Hubble constant is to get that piece better. And then, of course, the hard part is measuring the total mass density of the universe, as I'll talk about. But I would leave it here if this were a normal group, but you're not a normal group. So if you don't mind, I'm going to teach you general relativity in the next 2 minutes. Okay? We're going to derive Einstein's equations for an expanding universe. You can write your friends back home at the end of this in the next 2 minutes. Okay? It's really quite simple. Okay. So that's the picture I gave earlier, and I said, let's consider a galaxy of mass m at the edge of a region of radius r. What's its total energy? Well, let's actually do the equation. There it is. Okay, its total gravitational energy is a half mv squared minus gmm over r.
And that's still Newtonian physics.
Now, all we care about is whether this is positive or negative. We don't care about how big it is. We just care about its sign, right? Okay. Everyone's taking notes now. I like that. Okay. As long as you listen. So, I can make it simpler. I can multiply both sides. As long as I multiply both sides by positive numbers, I'm not changing anything. So I multiply both sides by 2 and divide by m. M is a positive number. And I still get, if this term is positive, then this galaxy has total positive energy. If it's negative, it has total negative energy. And so I compare it. It's just velocity squared minus 2gm over r. Well, okay.
So it's just a bit of mathematical manipulation. He's changed that equation to make it look like that one.
Okay, but we can plug in, because Hubble tells us what the velocity is of a galaxy at a given distance. Velocity is proportional to distance, and the constant of proportionality is h. So I can write velocity squared as h squared r squared. Okay? If v equals hr, v squared is equal to h squared r squared. Now, what's the total mass in a sphere of radius r? Well, what's the volume of a sphere?
So what he's done is just doing a bit more mathematical manipulation. Got terms like that on there, rho, and that's density. So it's just mix things around. And by Hubble's law, velocity v, speed, is equal to hr. So he's taken v squared there as h squared r squared. So it's all just manipulating this maths around a bit.
Anybody? Your hotshots. Don't be afraid. What's the volume of a sphere? Of radius r. Let's just... Squared. Okay, I'm so happy someone had the bravery to shout that out. Okay, you all knew it, but you were all afraid because just in case you got... Anyway, 4/3 pi r squared. Okay? And then, so the mass within a radius r is 4/3 pi r squared, the volume times the average density. Okay, you're all with me? Nothing mystical so far? So now I just want to make it simpler. So I want to multiply and divide by other positive quantities. Well, r squared is a positive quantity, so I can divide by it. And I get this quantity. Okay? This quantity, which determines the total energy of the universe times some factors, or total energy of that galaxy, I should say, is h squared, the Hubble constant, minus 8 pi g3 over rho. Well, let me just call all of these constants here, the 2 e total m, give it a name, call it minus kappa. We'll call it 2 over m e total minus kappa. Minus kappa over r squared, this constant, some number, related to the total energy of that galaxy, is h squared minus 8 pi g over 3 rho. This is Einstein's equations for an expanding universe. You have now derived it with all the factors of pi and 3. This is the equation that determines the evolution of the universe.
So there you have it. You're starting off from Newtonian physics and just manipulate the maths around a bit, change a few terms around, like saying v squared is equal to h squared r squared, and changing things around a bit there, you end up with general relativity equation. So from Newtonian physics you can end up with the same sort of equation as general relativity.
But what we call this quantity kappa in general relativity is the curvature of the universe. So in general relativity, we derive this equation in a little bit different way, and we derive an equation that tells us how the universe is going to expand, and it depends on the curvature of the universe. But now you see the physical meaning of curvature. We call this minus kappa. So if the total energy of this galaxy is positive, then kappa is negative. We call that an open universe. If the total energy is negative, so that this object will collapse again, then kappa is positive. We call that a closed universe. And if the total energy is precisely zero, so kappa is zero, just the amount of energy you would need if you had a coin throwing it up to escape and not move at the end, we call that a flat universe. And so this is literally, with all the factors of pi and 3, Einstein's equation for an expanding universe, and the problem is just to determine kappa, the curvature of the universe. And so we could draw pictures, but of course it's hard to draw pictures of curved three-dimensional universes because we're three-dimensional beings, and therefore we can't really picture curved three-dimensional surfaces. But we can all picture curved two-dimensional surfaces. So as a guide to the eye only, I draw you. It turns out the geometry is the same in 3 dimensions as 2 dimensions. There are 3 possibilities. Here's a 2-dimensional closed surface, the surface of a sphere. 2-dimensional open surface, an infinite saddle-like structure. And a 2-dimensional flat surface, an infinite piece of paper, flat piece of paper. And the business of cosmology was to determine what is the curvature of the universe, which universe do you live in, and that, of course, depended upon those quantities, the expansion rate and the density. And what is interesting is, if matter is all there is in the universe, then if we live in a closed universe, equations of general relativity tell us the universe will expand, stop, and eventually recollapse. If we live in an open universe, it'll expand forever. And if we live in a flat universe, it'll expand and slow down and stop. If matter is all there is. Why? Because in a flat universe, the total gravitational energy of every object is zero. So the positive and negative piece balance exactly. It's like throwing up a coin. It'll asymptotically escape, but never at infinity, it'll have zero velocity. Whereas if we live in an open universe, the total gravitational energy is positive, and just like a coin, it'll keep going forever. In a closed universe, it's negative. So all of this fancy geometry that sounds so good at cocktail parties and everything else is just first-year physics. And the question is to determine the total energy of every object in the universe, and that comes from determining the density of the universe for the following reason. Let me write that wonderful Einstein's equation down again. And look at one particular value, 0, a flat universe. Well, it's 0 when this term exactly equals that term. When that term equals that term, this is the expansion rate of the universe, this is the density. So the density of the universe is some critical density, we call it. It's a flat universe. If the density is less than the critical density, the universe is open. If the density is greater than some critical density, the universe is closed. And so we codify that by asking what the actual density of the universe is over the critical density, and we call that quantity omega. We call it omega because we want to sound scholarly, and whenever physicists have an important quantity, they give it a Greek letter to make it sound fancy and confuse others. And so
there you have it. This equation of general relativity can be derived from just a manipulation of an equation from Newtonian physics. And then it's all just playing around this new term here, kappa, and you think, what is the geometry of the universe? Well, in Newtonian physics they weren't considering that question, so it's trying to interpret these terms in a different way to what Newtonian physics has it as, but it's still a Newtonian physics equation. And so you are starting from Newtonian physics and you're getting the maths of general relativity. I don't think that is really highlighted that much by these physicist people, that all they're doing is manipulating equations around a bit and giving it fancy names and giving it fancy symbols, like the case down here. Decided to give that a fancy symbol. So Newtonian physics and general relativity are quite closely connected. There are of course other problems like how Newton deals with mass. We could start arguing that in relativity mass is not being dealt in the same way, but you're starting from a maths of Newton and you're still ending up with that maths but manipulated a bit in a different way and then interpreted a bit in a different way. So that's what I was trying to emphasise here in this talk. Thank you.